We're going to take a look at lesson 1.4. It's titled Avoiding Empty Pockets. It's page 47 of your textbook. This is going to deal with using exponents and order of operations. This lesson is a little bit interesting because the group work actually comes first. So hopefully you've done the group work, pages 47 through 50. We're going to start with the classwork that's on page 50, using some of the stuff you did in your group work. So let's talk about the box right above the group work to make sure we're all on the same page here. This is page 50, the box with the purple title. It says the difference between linear and exponential growth. This is a pretty important concept to know. From what you did in your group work, it says in account 1, the simple interest account, the values grow by adding the same constant number. This is called linear growth. In account number 2, the compound interest account, the values actually grow by multiplying by the same constant number. This is called exponential growth. Under the classwork, it gives us some questions. Number 1 says, here's a key observation about repeated multiplication that occurs when finding the value of account 2 in the group activity. Repeated multiplication can be expressed more concisely by using an exponent. It's a shorthand way of writing repeated multiplication. Let's continue working with the two accounts from the group portion of this lesson. With an initial investment of $1,000 and 5% compound interest, the value of that account after 7 years would be given by the expression below, 1,000 times 1.05 to the 7th power. Without using our calculator, let's write that expression without any exponents. So I write the 1,000. How many times do I have to write the 1.05? Well, the power tells me to write it 7 times. So I'm going to write 1.05 7 times, if I can fit it on my screen. 2, 3, 4, 5, 6, I can just about fit it in, 7. That's what that exponent means. So these two expressions in under number 1 and number 2 mean the same thing. Number 3 then asks us to actually figure out the value of the account after 7 years. At this point, you want to put it in the calculator, either as the expanded one or as the one with the exponent. The answer should be around 1,407 and 10 cents. Number 4 says in account 1, where the interest is simple, the account value goes up by 0.05 times 1,000 or $50 each year. Write a calculation that would find the value after 7 years, then actually find the value. I'm still starting with $1,000. But now I'm adding $50 per year for how many years? 7. So 50 times 7. Either throw that into your calculator or do it by hand. Your value for the simple interest for this account would be $1,350. Let's move to page 51. It says, let's take a stab at summarizing what we've learned about linear and exponential growth. Use the calculations for simple and compound interest as models. With linear growth, the value after a certain time is calculated using the starting value plus a constant times a certain number of time periods. With exponential growth, the value after a certain time is calculated using the starting value times a growth factor raised to a power. Number 7 says, without trying to give away the answer to question 6 too much, part of it involves a power. What is the significance of the exponent? In exponential growth, what does the exponent represent? It represents the number of time periods. In the purple box, they summarize all this for us. It says when a quantity increases based on linear growth, the value after a certain number of time periods can be calculated using this pattern. The new value equals the original value plus the amount of growth per time period times the number of time periods. When we're looking at exponential growth, the value after a certain number of time periods can be calculated using the new value equals the original value times 1 plus the percentage raised to the number of time periods as an exponent. Number 8 says, use what you've learned about linear and exponential growth to calculate the value after 20 years in each of the accounts we've been studying. Write out all the calculations that we did. So for account number 1, this was the one that had linear growth. I started with $1,000, and I'm adding how much per year? We are adding 50 per year for how many years? 20 years. How much will be in this account after 20 years? $2,000. Let's get a different color for account 2. In account 2, we did start with 1,000 again. But this time we're multiplying by 1.05. 5% was the growth factor. How many time periods? Well, it's for 20 years. That's going to be my power. You're going to have to put that in your calculator. Your calculator is going to tell you that at the end of 20 years, you have 2,653 and 30 cents. I don't know what my calculator, my phone, my pen just did something weird. See what we can erase here. That'll work. So 2,653 and 30 cents. You can see that exponential growth is the way you would like your money to grow. It does grow faster. Turn the page to page 52. They're going to have us work with this a little bit. Number 9 says if you borrow $500 at 3% simple interest, the amount you'd owe after 4 years is given by the expression. How much did we borrow to start with? Well, we borrowed $500. And what is the interest rate? 0.03. Make sure you do know how to convert percents into decimals. 3% is 0.03, not 0.3. That would be 30%. Number 10 says to correctly evaluate the expression, you'll need to remember the order of operations, which says that multiplication comes before addition. Go ahead now and evaluate the expression from number 9 to determine how much you would actually owe. Throw it into your calculator, figure out how much you owe. You should find that you owe $560. Number 12 says, go ahead and do what's down here instead and see how it compares. So if I were to do this using order of operations, I would first of all multiply this. So I'd get 500 times 1 plus 0.12. Again, following order of operations, I do what's in the parentheses. I would do 500 times 1.12. Then finally calculating that, I do get $560 again. So calculating a slightly different way, we still got the same answer. They ask us in number 13, the reason you get the same answer is because of a certain property we have. That property that we have is the distributive property. 14 asks you to come up with an example of the distributive property. Here's a real quick example. If I have 5 times 3 plus 7. Two ways I could do that. I could do it using order of operations, which would say I add first 5 times 10, which is 50. Or I could use the distributive property. Let's rewrite the problem down again. The distributive property says that I multiply everything inside the parentheses by the number outside the parentheses. What is 5 times 3? 15. Plus what is 5 times 7? 35. When I add those two numbers, I get 50. Let's review real quickly the order of operations. I feel like we need to make sure you know it. Do it over on the side here. The order of operations, a lot of people remember it as PEMDAS. And what that means is parentheses come first, exponents, multiplication, and division. Neither one of those is more important. If division comes first, it gets done first. Addition and subtraction. Same deal. Addition is not more important than subtraction. If subtraction comes first in the problem, it gets done first. If you need a further review on order of operations, you can probably find it if you just Google order of operations. There's probably lots of apps out there that'll help you practice with it.